Thanks. Okay, so, but you could hear me anyway, right? Sure, sure. It was the secret stuff. So yeah, so this is more about how one might. So if someone wants to run Infer in on a large code base on in a continuous integration system, then you might want to know about certain things and also understand how some things are designed in Infer, so that you can get the most out of it. So that's the kind of overall idea here. So I'll first talk about what probably most people who have used Infer know already, the basic phases of a run. Then I'll go into what a few things, a very high level overview of capture and how the integrations work at a sort of abstract way, and how one might parallelize more capture as applied to their situation. Then look at the analysis where, as we've already heard, especially from Jules, how the on-demand analysis works. It was very, I think what Jules didn't have a lot of time to go into is how do we parallelize that bit and the various different options that exist today to do that. Following on from that, so that's already something that exists in Infer, and you can control that when you run your experiments and so on. But the next level up is how do we distribute that analysis over several hosts, not just one that has multiple CPUs or cores, but over a larger, a set of hosts if your analysis needs go there. And then how we can get better, again, better performance in doing that by being intelligent in how we partition the work that we distribute. So that probably everyone, like I was saying earlier, probably most people might be familiar. This is the sort of basic flow that you have. You have some, it's assumed that you have some build system, your code base has some build system, right? Or it's maybe just a compiler that you run. Here I've written modified files, but really that should mean maybe a subset of the files that your code base consists in are of interest to you. Maybe you don't want to analyze everything in your code base, so maybe that's a commit. So you only want to analyze starting from a small set of files and then branch out as needed. And the first thing that will happen is what we call capture, which is really the equivalent to compilation or building your code, but here it means that Infer plugs into that and gets all the SIL and CFGs out and stores it into its own databases, so it can then consume it during an analysis, which is where the magic happens. And then finally that outputs procedure summaries and error logs, which are here separated just for the purpose of making it clear that essentially when Infer runs the analysis, the summaries are produced and also consumed because of compositionality. But we also generate logs of what are the errors that are found, and then these are consumed by the phase that takes all that and then produces error messages, traces, and so on and so forth. Typically, analysis and reporting are done in one step currently. And you actually have to, so by default, reporting happens automatically after you do the analysis. You can stop that if you want. There are flags for everything, but that's the main flow. Okay, so capture here, obviously it depends, obviously it depends on the language that you have, that your code base is in, but it also depends on the build integration that your code base has, right? So you could have just a plain compilation command, and that should, by the way, these commands here make it clear that we're only running that particular phase, right? So we're only doing capture, we're not doing analysis or reporting or any of that stuff, right? And yeah, so if you were after a few files in C, then you might do this, and that will make Infer use a particular integration that's adapted to Clang, and run its plugin, etc., etc. So it's a very, it's a language and integration dependent flow. Similarly, with this would work for compiling a Java file. And I've included that actually because I know that loads of people have been asking, oh, I have a jar file or I have a class file. I have already built that bytecode, and because Infer actually consumes bytecode, doesn't really consume Java source code, contrary to what Clang, the Clang integration does. This is how you might capture that bytecode directly if you were in that case. Anyway, the point is that these three are, let's say, the root integrations that are very language dependent, and on top of those you would have integrations that run some build system, and then Infer has to plug into that by in various ways. In the make integration, what it does, for example, is that it pretends it is the actual compiler. So when make runs, instead of running Clang, let's say, it would run effectively a version of Infer that is standing in for Clang, and then Infer would produce the same sort of side effects that Clang would do by also running Clang, but also it would get all the flags it needs to run its own capture directly. And there are other integrations like Buck, Gradle, Maven, etc., that exist in the Infer repository, aren't all used by us and maintained by us, but yeah, and it's possible to write more. Yeah, that's more or less the gist. Okay, now this is what, so if you, let's say you have some build system, but you have a large code base, or you want to integrate in your CI, and your particular build system, when combined with Infer, leads to poor execution times. What can you do? You could just say, okay, I give up, or this is how it is. So the problem is that when you use the build system, let's say we have make here. Essentially, this is a dependency graph of the targets that your build system might have. Essentially, the parallelism here is bounded by the build system itself, right? So you cannot have more infers running concurrently than, let's say, 2 for this graph, because that's the width of this graph, right? So the build system forces the leaves to be built first, and then it crawls up, climbs up the graph, right? And that might make sense when you're doing compilation, but it doesn't necessarily make sense when you're capturing with Infer, because really you're not going to be building a binary here. right? So you don't need necessarily this dependency structure. What you want is just to syntactically consume all the source files, right? So in this case, using the build system might be a bit counterproductive in terms of how long it takes to run the capture. And so the idea is that if you can break down this, let's say, per individual target, and that, okay, there's a bit of an asterisk here because the idea is that that assumes that each of these targets is buildable without the dependencies necessarily being there. Okay, so this is a bit tricky, but let's say we had some graph that we could cleanly chop up into more subsets. Then we could do the capture individually in each of these sets, and then merge the results all together, which is a very, so all this could be done in parallel, whereas this is a very relatively fast sequential step, right? So, yeah, so that would mean you could capture all these in parallel, like I said, and then do the merge. The buck and Gradle integrations are in Infer are written exactly using this technique. So, for example, the Gradle, it will do some magic by running Gradle itself and then consuming its debug output. But then essentially what it will do is that it will recompile all the files, all the Java files, using the commands it has found in the debug log. But it will use the Java-C, essentially this line here for each one of the files, right? And all these can be parallelized, right? There's no dependency necessary, structure necessary here. So they will all be built essentially in parallel and then merged into one capture database at the end. Yeah?
Could you detail what you mean by merge?
Right, yeah, that's a good point. So merge means so here, this is the output directory of each command, right? So we build, let's say, n targets, we end up with n output directories, and each output directory has a capture database inside. It's all SQLite. The capture databases contain CFGs and type environment information, essentially, and source file information. And all these will be essentially unioned into one database with this command that will end up in this output directory. And there are some subtleties about what happens when you have duplicate occurrences of procedure names or file names, and the this algorithm that does the merge has some logic where it won't just blindly overwrite one duplicate with another, but it will try to make sure that any structured information contained in there will be unioned essentially into the final database. Okay, let's go to the perhaps more interesting parts, which is the analysis. So here, here we have some files to analyze, right? So again, I remind people that we don't have to, when we capture a code base, we don't have to always analyze all of it. We can be more, we can have a narrow targeting of the files that we want to analyze. So here we have some set of files. We give it to the scheduler, and the scheduler will do its thing and essentially prepare some partition, do some, let's say, distribution of work computation into work packets, and it will start processes, concurrent processes that each one will do analysis, and it will then distribute the work packets accordingly. That's just standard parallelization. And here I've just put the capture DB that is being read by the workers and the analysis database that is being read and written to to write summaries and so on, and error logs. So currently there are 3 schedulers available. I'll go through them in the next slides. And you can control the number of workers. And that's the kind of high-level picture here. So the file scheduler, which was the first scheduler that ever existed, and in fact it wasn't even called a scheduler back then because it was kind of the way it was done, essentially takes as a work packet every source file that is in the set of files to analyze, right? So and what it does, so each file gets sent to one worker, right? So here we have 2 files, and the worker essentially reads the list of procedures in every file and then says, okay, let's analyze each procedure at a time, right? Sequentially within each worker until I finish. Right, that's the very basic stuff. One funny thing about it is that it allows races over summaries, right? So let's say we have scheduled here these 2 procedures in red. That's a common dependency of both of them, transitively speaking, right? And if timing is, if the timing constraints are just right, then both workers will end up analyzing the same procedure concurrently and even write the summary twice, right? This isn't too bad in terms of correctness because most of the time we're deterministic, so we should write the same summary, Here, as even though we may do that several times, but it's not great in terms of worked application and parallelization of work because, we're basically, if we could have done it in one worker, then why do it in several, right? And there have been, we have observed pathological cases where, especially when, where multiple workers would go down a very long chain and race all along the chain, right? So they wouldn't just be one summary that they race on, but a whole, or dependency graph, in fact, right? A whole cone of procedures that they would race and duplicate all that work. So, so that's one deficiency or one disadvantage. The advantage is that it's a very simple one, right? So, there's advantages in simplicity. The other disadvantage that for some use cases is that the granularity is coarse, right? So your work packets are the files that you want to analyze. So if you have very few files that you want to analyze, that's your maximum parallelism, right? So you can't go any faster than that, any more parallel than that. So if it's in a CI, for example, if it's in a continuous integration system where your commits have 1 or 2 modified files and you start from those files, then you're not going to buy a lot of performance like that. So, yeah.
Is it possible that 2 workers are working on the same file?
No, but they might work on the same procedure that is, so, okay, so this is why I've put this upward arrow here, right? So you, actually you could even have, so the arrows can be anywhere, right? So you could have this worker working on that procedure and this worker working on that procedure, right? But they wouldn't have the same work packet, right? Each file as a file goes on to one worker only, if that makes sense. Okay, so then the first step we took was to to use the static call graph in order to partition the work at the level of procedures and not files. Okay, so what we do here is that we go through the static call graph. We build the static call graph. And what is the static call graph? Is basically what I mean by static call is the calls that are non-virtual. They are explicitly in the CFG of each procedure. Okay, so we read those and we construct the static call graph. Okay, here I've used dotted lines to represent the dynamic dependency or real analysis dependency, and the solid lines to indicate the static call being present in the code. And once we do that, we can say, okay, I'm going to take all the leaves. I'm going to schedule them first, right? The leaves meaning they have no dependencies that are not summarized, let's say. Right? I'm going to analyze these first, the procedures in red. And when I'm done, I'm going to climb the graph gradually until I'm at the top, right? And because these procedures, well, first of all, they are procedures, they're not files, so the granularity is much smaller. We're going to have loads of them. And it's a frontier that will climb the graph, so the width can be high and we can get better parallelism, so that would help with performance. But there is the problem of dynamic dependencies. What do the dynamic, so does that affect soundness? Well, no, because we are still using the same on-demand analysis, right? So if we are asked to analyze this procedure, we will necessarily analyze that as a dynamically, as a dynamic dependency, right? It's just not going to be in the static goal graph, so we're not going to be any wiser in terms of performance scheduling, right? So that's one issue here with the dynamic dependency graph. It does reduce races, right? Because of the way we climb the graph. If there was no divergence at all between dynamic and static, then there wouldn't really be any races, right? Because we would always be scheduling distinct procedures that have no dependencies, right? And that means we should never send the same procedure to two workers, right? However, when there are dynamic edges, and they do exist a lot, and I should add, because I think we haven't mentioned this up to this point, it's not just calls, it's also whatever any analyzer may treat as a dependency, right? So examples are, so for example, the deadlock detector would say, okay, I see I'm locking here a lock that is stored in some class A. I will go and also retrieve all the summaries of the methods of A to see if there's any deadlock, right? Which means that essentially we have edges inserted to all the methods of A where there are no static calls in this current procedure that I'm looking at. Okay, so it's not just calls, it's anything an analyzer might request as a dependency, and so these are even more of, they occur even more often than just dynamic or virtual calls. Okay, and what happens with cycles? Well, because if we have a cycle, obviously that's never going to have any leaves inside it, right? So how do we analyze the cycles? We basically leave them for the end, and then it's as if we were using the file scheduler to go through them, right? So we just fall back on the stuff in the previous slide for the cycles. Yeah?
Yeah, I have a question about the static call graph. So you just take into account static calls. you don't try to over-approximate virtual calls by type informations, because, for example, in Java, you see a virtual call to M, but in fact you see A.M, and maybe, so you know that there will be a subclass of A, where M, and sometimes it is A itself, so it's not bad to use it. Maybe so it's not true, but it's not bad to take into account this type
so you're
proposal.
Saying where we have a static call, well,
where you have a virtual call, you could guess.
Virtual call, so I think in the current situation, it is treated as a static call to the static class to the static type that is seen in the. So we don't analyze the whole hierarchy, but we at least consider that as a call to the static type. We could, but that would add potentially a lot of more edges here. I don't know whether that's, we've never tried that. Okay, and the last iteration on trying to build more performant schedulers was, just look at the time, okay. Is the restart scheduler, where the idea here is that we schedule at the level of procedures, so we have high granularity. We schedule the procedures in the files that we want to analyze, so we don't look at any graph. We don't do any pre-computation of the graph. So here I've put, let's say we have just these two procedures to analyze. So we start analysis from those, and we just, every worker will take one of these, and then we'll start an on-demand analysis as usual. But what happens is that when a worker starts analyzing a procedure, it will put a lock on it until it has finished writing its summary, and that's when it will unlock it. So what happens is that, let's say this worker starts, it will lock this procedure, it sees that there has a dynamic, it has a dependency on this procedure, it will go down, it will take a lock on that procedure as well. Okay, so these two have been locked. And meanwhile, this other worker starts analyzing this procedure, locks it, goes down the graph, says, okay, I need more, goes here, and then it tries to lock, but then sees that the other worker has the lock. And what it will do at that point is that it will fail the whole work packet. It will pop essentially the whole call stack, unlocking along the way. And then when it goes back up here, it will give that work packet back to the scheduler and say, I failed to do this, please reschedule this and give me something else to work on. Okay? And the idea is that this eliminates essentially almost all the races. Theoretically, it completely eliminates the races, but practically there's some double-checked locking that we should do and we don't, because it's very poor performance. So we have, like, I don't know, a few procedures in the thousands raced on. So we don't have any more worked application because of the races, but essentially we have some worked application that happens in time, right? Because when we fail due to a race, we have done some work that will have to be redone the next time the worker will, the next time the same work packet is scheduled again, right? So every time a work packet is failed, some work gets lost because it wasn't written to disk, and therefore we have to redo it next time. And it may live lock with highly recursive code. Okay, so we have some, so if you imagine big cycles and two procedures on the cycle on opposite ends getting scheduled to different workers, right? So they might go around the cycle, and then realize that both of them cannot progress, right? Because the other, well, it shouldn't happen that both of them do, but it might happen depending on the scheduling. So yeah, so we might have a lot of restarts essentially, and possibly even live log. There is some code to detect that, which is that basically when we send a work packet back to the scheduler, we say, okay, this is the summary I failed to take the log of. So don't reschedule me until that has finished being analyzed, and that reduces to some degree the risk. Okay, so that's all about what happens in a single host when you're doing analysis. Now, how can you distribute analysis if you have a large code base that one computer is not enough? So one way is that you can do your capture, okay, get all the source files that were captured. Okay, so now I'm not going to talk anymore about analyzing just a subset of files in your capture. I'm just going to talk about analyzing everything, okay? And then split that list of files in as many sets as you have hosts. Okay, so just build a long list of source files and just partition them however you want into different sets. And then copy the capture database that you got to all the different hosts that you have. And then in each host, pretend that you're actually not analyzing all the files, but just the set that you got from your partition. Okay, so you run n analysis, one for each set, separately, but starting with the same capture database. Okay, so it's like a broadcast model where you copy the capture database to all the hosts, and then once you're done, you collect all the output, the result directories, and remember that reporting happens on every host, so reporting has happened already. We just need to merge the reports, and that's there is this extra machinery that you can use to just essentially JSON merging. You could do it by hand if you wanted. So that's a basic distribution model. Very kind of simple. The one disadvantage that you get with this is, again, worked application. This time it's not exactly a race because we're not racing over the same data store, but you may end up analyzing the same procedure on multiple hosts because it is a transitive dependency of two files, let's say, and one file has gone into one host and the other file has gone onto another. Okay, so both hosts would then be obliged to analyze that same procedure twice. So for that reason, we have added some facility that can do the partitioning in a more intelligent way to reduce the worked application. So the idea here is that we're going to go to the static call graph, right, to do this more intelligently. And we are going to build a version of the static call graph, but on files, not on procedures. And the main reason for this is that we're using all the machinery we have. We're not really able to schedule specific, to ask for specific procedures currently. This option, the changed files index option, really is a set of files. So we assume that the granularity will be at the set of files where you do your partition. And so therefore the static call graph will be at the level of files. Now, the lift to the file level is kind of trivial, right? But that's not necessarily going to lead to a good partition later on. So so here we have 3 files, okay? And I have drawn some dependency arcs. what happened is that if we lift in a trivial way this relation to files, then we're just going to end up with an arc here, an arc there, and an arc back. But this doesn't really represent how much work is entailed to cross these edges, if you like. You know, how much does this file need that file, all the summaries in that file? Okay, that's not captured if we just lift blindly. So what we do instead is that we put weights, and the weights are the number of distinct callees in the target whose summary I need in the source. Okay, so here everyone is calling, in this file, everyone is calling the same procedure, so the weight is going to be 1. Okay, and the idea of not counting the number of times, but rather the set of distinct callees is that because they're going to be cached anyway, and they're going to be analyzed just once, there's no point counting their number, just, counting the number of calls, but rather the number of distinct targets. So here the weight would be 1, here the weight would be 3 because we call 3 distinct, and the back arrow will just have a weight of 1. Okay, so we build this graph, and then we, of course, we're going to end up with cycles, right? Because we lift up to file level. So the first thing we do is we make that acyclic by deleting minimal edges. And then we do a sort of spanning forest computation, again, by deleting minimal edges. And then essentially we have a set of trees, and we try to distribute these trees in the workers that we have. So each worker will end up with a set of trees to analyze. And then we do an extra step where we try to make sure that the resulting total number of files sent to each worker isn't too divergent across the set of workers, so we don't end up with one worker having to do everything and then all the others just analyzing a single file, because of course that would mean that the wall time would not benefit, right? If we have imbalance between work packets. So we do an extra step where if the imbalance is too great, we keep removing edges until from the largest trees until we can spread them sort of equally. So this step here would be inserted essentially in this place, in this procedure, to do the partition more intelligently, and then the rest would work as is. Okay, and that's all for me.
Hi, thanks for the talk. So for the intelligence partition part, I'm thinking, is it possible to not partition the whole program by the physical file? I mean, you can make it like a virtual file, which is not really the procedures belongs to get a better edge between them. But I'm not sure if this will introduce another more difficult problem, like how to partition. So I'm not sure if this is have you guys tried that or something? Yeah.
No, it's a good point. So I think if we added infrastructure for selecting specific procedures to, when we start the analysis, can we tell Infer, I want not just this file, but this particular procedure in the file? If we did that, then this whole thing, I think, would just work out of the box, because the same algorithm will work for procedures, right? It's just that we will not have the weight information in the same way, right? I don't know how the... Yeah, and I don't know. It's a very heuristic issue, right? How to distribute the work. So it could be that it's a good approach, or it could be that it doesn't make a huge difference if already we have a large number of files. So if we distribute the files themselves we end up, having a reasonable distribution at the end.
Yeah, I see. Thank you.
Yeah, I was wondering, so how much of this work is front-end independent? If someone write a new front-end, does he have something to configure, or is it just for free?
You mean this bit, or
all the infrastructure about
well,
capture analysis?
I mean, the front-end specific stuff is just this bit, right? So yeah, just this bit, in fact, right? Everything else is generic in at least the front end, and in fact, both the stuff about scheduling as well as distribution carry over. However, the efficacy will depend on aspects of the language. So as an example, dynamic languages mean, a highly dynamic language like Hack essentially means that the static call graph here is worthless, right? And that means this is as good as round robin partitioning or random shuffling, right? Which is, it's not terrible, but it's not great either. And that's also one aspect about the schedulers, right? It's the same idea here, is that if the static call graph is not very representative of the final result, then you're probably better off using the restart scheduler, and vice versa.
Okay, so maybe another one. And Infer is meant to be used as an incremental static analyzer. Any idea to use incrementality for the scheduling?
Yeah. Jules wrote this replay scheduler, right? I don't know why we don't use it, but so yeah, okay. So currently, when we write a summary, the summary includes the actual dependencies that were used to compute that summary, right? Because sure, we don't know these when we start analyzing a procedure, we don't know what this might be yet, right? We can only guess by the static call graph. But when we finish writing the summary, we know. We know the exact things we needed, right? So we do write that information in the summaries. And so we can reconstruct, after the analysis, we can reconstruct the true dependency graph, right? So if we were in a continuous integration system, we could say, okay, I'm not going to use the static call graph to schedule. I'm going to use the call graph scheduler, but I'm not going to use the static call graph to schedule my analysis. I'm going to use the last true, real dependency graph I got for these files the last time I analyzed them, right? Or some, approximation of that. So that might work a lot better, in fact, than the call graph scheduler as it is now. But we haven't done that yet. And also, you mentioned incrementality. There is an incremental analysis feature in Infer, which I didn't talk about. And it will work. So if you have run an analysis and you immediately want to run an analysis on a slightly changed version of your code, there is a feature that will will do exactly this, use this idea of reading the true dependency graph and then trying to invalidate only the summaries that have, that are known to potentially have changed or to not, no, what's the right word? It will invalidate it will keep all the summaries we know for sure could not have changed. Let's put it this way.
Okay. Thanks again, Nikos.